Banker's algorithm. Banker's algorithm is a resource allocation. Hello everyone, Banker's algorithm. Today is our topic. Let us see what is Banker's algorithm. Banker's algorithm is a resource allocation and deadlock evidence algorithm. It is used to say that the process are in deadlock or not in deadlock. Let us see what is Banker's algorithm. Banker's algorithm is a resource allocation and deadlock evidence algorithm used in operating systems. It ensures that a system refines in safe state, carefully allocating resources to the processes while avoiding unsafe states that could lead to deadlock. Means here the safe state states that there is no deadlock in the system, and unsafe states that there is a deadlock in the processes. Let's see the next point. The Banker's algorithm is a smart way of the computer systems to manage how the program uses resources like memory or CPU time. That means the resources, how the efficiency of the CPU time they are going to utilize, it can say by Banker's algorithm. And it helps to prevent the situations where programs gets to stuck and cannot finish their tasks. Means if a system is going to struck by some X processes, it's can't going to complete the process reallocation completely. So it can help and it can lead to take the deadlocks. Let's see next point. As components of the Banker's algorithm, let n the number of the processes in the system and the number of resources are available. There is an available. It is an 1D array size and indicating the number of available resources of each type. Available of array j equals to k means that the k instances of resources of type rj. Rj is nothing but resource. Next, max. Max is nothing but number of possible resources that can allocate. It is a 2D array and star m that defines that maximum demand of each processes in a system. Max I comma j equals to k means pi may request at most k instances of resources type rj. Means k instances of the resources are counted by r. Rj means it can be r1, r2, r3. Later on, allocation. It is also in a 2D array of the size m star n that defines that number of resources of each type currently allocated to each process. That means allocation is nothing but already it can have. Max means it can able. So what's the next one? Need. Need is also in a 2D array. The need is nothing but max minus allocation. Allocation specifies the resources currently allocated to the process PI, and need specifies the additional resources that process PI may still request to complete its task. Allocation is nothing but it can have that resources in that particular process, but it can need to access some more other processes to complete its tasks. Let us see key concepts of Banker's algorithm. There are two key points already we discussed in previous. One is safe state, and the other one is unsafe state. What is meant by safe state? There exists at least one sequences of process such that processes can obtain the needed resources, completes its execution, release its resources, and thus all allow other process to eventually complete without entry to deadlock. Means it is nothing but safe state is nothing but there is no deadlock in the processes. Whereas unsafe is nothing but there is can be deadlock and one process or two or three more processor cannot enter into a safe state. Let us see an example for unsafe state. Consider the three processes P1, P2, P3 and 6 instances of resources. Let us see. The available instances of the resource are 1. The current allocation of resources of the process is P1, P2, P3. P1 is going to allocate 2. P2 is going to allocate 3. P3 is going to allocate 1. The maximum demand, that is nothing but maximum allocation. That is P1 is going to allocate 4. P2 is allocating to 5. P3 is going to allocate 3. We already seen that need equals to max minus allocation. Let us see. So here there is a process P1, demand is 4, allocation is 2. So max minus allocation is nothing but need. So 4 minus 2 is nothing but 2. And P2 process, there is maximum demand is 5 and the allocation is 3. So 5 minus 3 is nothing but 2. And let us say P3, the maximum demand is 3 and allocation is 1. 3 minus 1 is 2. So P1 may need 2 more resources to complete its process, and similarly P2 also require 2 more processes to complete its process, and P3 requires 2 more resources to complete the process. However, there is only one resource available, even though none of the processes are currently deadlocked in the system in an unsafe state, because there is no sequence of resources allocation that guarantees all the processes can complete. Banker's algorithm consists of safety algorithm and a resource request algorithm. Let us see Banker's algorithm is made up of two parts. What is this? Safety algorithm and resource request algorithm. Let's see safety algorithm. The safety algorithm checks whether the system is in a safe state, meaning all processes can complete without causing the deadlock. It is nothing but safe state. Means every process should complete its process and no process cannot complete its process. Then we can say it is a safety algorithm. Let us see steps in safety algorithm. First step is initialization. Later on, work equals to available resources currently available in that particular processes. Finish high equals to false for all processes. None of have been finished yet. Before going to solve any sum, we should assume that every process is in false state. Next step 2, look for a process pi such that f finish I equals to false. That means finish I equals to false. As we taken, like we have to assume, because we are before going to the sum, we have to assume that it is false. Later on, if anything is satisfies the condition of need is less than or equals to 1, then we can update it to a true statement. Later on, step 3, if such a process is found, allocate resources to work equals to work plus its allocation. Mark the process finished. Finish I equals to 2 and repeat step 2 for remaining processes. If all the processes are marked finish, finish I equals to 2 for all, the system is in safe state. If any one of the process is not done as finish I equals to 2, then the system is unsafe state and there is a cause of deadlock. Next, resource request algorithm. This algorithm decides if a process resource request can be guaranteed safe. Step 1. Check if the request exceeds the process maximum needed. If request I is less than or equals to need I, continue. Otherwise, error. Check if resources are available. Request I is less than or equals to available, continue. Otherwise, process have to wait. Temporarily allocated the resources. Available equals to avail minus request. And allocation is nothing but allocation plus request. Need I equals to need I minus request I. Run the safety algorithm. If the new state is safe, grant the request. If unsafe, roll back and make the process to wait. Because we are going to roll back is due to we are ensuring that no deadlock should be come into the processes. In short, the resource request algorithm ensures resources are only guaranteed if the system remains safe, preventing deadlock. It is nothing but the system is remains in safe state. It says that preventing the deadlock means there is no deadlock in the system if the system was in safe state. If it is unsafe, there may be a deadlock, there may not be a deadlock. Let us see one example. Consider a system with processes of P0 through P4 and the three resources of type A, B, C. Resource type A has 10 instances, B has 5 instances, C has 7 instances. Suppose at time T0, following a snapshot of the systems has been taken below. As below there is a snapshot, you all can look at to this. There is a first column indicating that processor from P0, P1, P2, P3, P4. Allocation, they given A, B, C. A is 10 instances. So if you sum 0 plus 2 plus 3 plus 2 is nothing but 10. But we have to see in 10, 10. How many we get? A, 10. But here 4 plus 3 is 7. In available, there is 3. So the total summation is 10. Again, let us check B. 1, 0, 0, 1, 0. So 1 plus 0 plus 0 plus 1 plus 0 plus 3. The summation is 5. And let us see C. 0 plus 0 plus 2 plus 2. 1 plus 2 is nothing but 5. And that available is 2. So 7 instances for C. B has 5 instances. A has 10 instances. The allocation of respected processes are given below and the maximum is given below and the availability is 332. Let us see need matrices. We already discussed it previous that need is nothing but max minus allocation. Let us see. As we seen in before previous here that max of P naught is 753 and the allocation is 0 1 0. Already we know that need equals to max minus allocation. That means 53753 minus 0 1 0. It is nothing but 7. 5 minus 1 4 and 3 minus 0 3. That means need of V0 is what? 7 4 3. Is it there? 7 is from A instance, B is from 4, C contains 3. For every processes, the formula is same. Need equals to max minus allocation. Then B0 have 7 4 3. B1 has 1 2 2. B2 has 6 0 0. B3 has 0 1 1. B4 has 4 3 1. Let us see safe state and safe sequence analysis. Step 1. What is this? M and already we give it. M equals to 3, N equals to 5. Work is equals to available. What is the available? 332. Work equals to 332. First we have to consider false. If any process is satisfies the condition, then we mark it as true. Say step 2. For I equals to 0. What is the need of P0 process? 743. Finish 0 is false because need is greater than the worker. But what is our condition? Need should be less than or equals to the worker. So P0 must wait until the condition of need is less than or equals to work. It can satisfy. Let us see step 2 for process P1. What is the process P1 need? 1, 2, 2. What is finish 1 is false. We already assumed that it is false. Let us see. Need is less than or equals to work as the condition is satisfied. So P1 must be in safe sequence. So later on we should update and finish that P1 is true. Next, let's see step 3. What is that? Work is equals to work plus allocation. This allocation is nothing but the work is here is available. What's the first condition? The allocation is for process P1. So our new work is what? Work plus allocation. That is work available given is 332. This is the allocation of P1 200. So 332 plus 200 is 532. So finish is here. At process P1, it's going to change as true. Next, see for process P2. Need equals to 6000. Finish 2 is false and need 2 is greater than worker. So P2 must wait as the condition is false. Next for I3. Need equals to 0111. Finish 3 is false and need is less than or equals to work. The condition is safe. So P3 must be in safe sequence and it's going to update. So here what is the new work allocation? Work plus allocation. So 532 plus 211. So the new work is 743. So here at the finish, the process P3 is going to change as true. Again for step 4, I equals to 4. Need equals to 4, 3, 1. So finish 4 is false. So need is less than or equals to worker. So P4 must be in safe sequence. Later on, step 3. Here also the work is going to update and later after completion of P4, again we should come back to the new processes, that is P0. So at I0, what is the need? 7433. And what we have now available work? 745. So the condition is satisfied. So the new work is going to update as 755. Later on, which process is remain here false? P2. So P2 is 600, its need. So it's going to satisfy the condition because we have work available 755. So it also has been satisfies the condition. We are going to come to a new available work, that is 1057. So here what we observe at the first beginning, what the instances for the each resources are we are going to take, those are same. So what is the same sequence? P1, P3, P2, P0 and P2. This is the banker's algorithm. Okay, in before we have seen that banker's algorithm live example. Let us see code in Python. First, we are going to define a banker's algorithm. How many processors we are going to take? 5 processes from P0 to P4. What are they? P0, P1, P2, P3, P4. And n equals to 5. This can indicates the number of processes. R equals to 3 indicates the resources. We taken 3 resources that are A, B, C. A having 10 instance, B having 7, C having 5. What is the allocation of process P0? 0, 0, 1. What is P1? 3, 0, 0. What is P2? 1, 0, 1. What is P3? 2, 3, 2. What is P4 allocation? 0, 0, 3. Later on, max allocation of P0, P1, P2, P3, P4. Here, P1, P0 is nothing but 7, 6, 3. P1 is nothing but 3, 2, 2. And P2 is 8, 0, 2. And P3, 2, 1, 2. P4, 5, 2, 3. What is available? 2, 3, 2. Those are available resources. Next, F equals to 0 star n. N is nothing but number of the processes. Answer is nothing but 0 into n. And index is nothing but 0. Need equals to 0 into R, resource, for I in range. For range. For I in range n. For j in range R. R is nothing but resource. N is nothing but processor. Here need I j equals to max minus allocation. We already know this formula. Need equals to max minus allocation. Let us see y equals to 0. For k in range n, for I in range n, if f of I equal to 0, flag equals to 0, and for I in range of R, then if need is greater than available, flag equals to once. That means it is indicating that it's the true condition. Then break. If flag equals to 0, answer of index, that means which process equals to I. So index plus equals to 1. For y in range R, available y plus equals to allocation of I comma y, because we are going to change the new available work. So it's going to change. So f of I equals to 1. So it can print that the save sequences in the sequences of the follows. So for I in range n minus 1, print f p answer of I. So end the statement. So print answer n minus 1. This is nothing but banker's algorithm. It is very easy because in banker's algorithm there are only two conditions. One is safe condition, one is unsafe condition. Here we done a code now. For this the output is this is in a safe sequence. How this is going to execute? P1 process, later on P3 process, later on P0 process, later on P2 process, and later on P4 processes. The main condition here is this while loop is going to deal in the code. Thank you.